Yeah, hello everybody. Statistics, and we are just in the revision of the basics of statistics, so I can catch everybody, and afterwards we can start with a more detailed discussion of hypothesis testing. So we have talked about general describing a data set, calculating means, median, dispersion measures, and then the so-called contingency tables, and then we jumped into the theory. And for this, at first, of course, we had to define what is understood by a random variable. This, of course, you have also heard in your introductory courses, and then also hopefully you have talked about the difference between discrete and continuous random variables, and that especially then you have to interchange the probability mass function with the density function, and this is then going through the cumulative distribution, what is understood by the expectation value there. In general, we just interchange the summation operator with the integration, and then of course the most important dispersion measure, the variance, as the sum or the integral of the squared distances with respect to the expected value. And there later on in hypothesis testing, we use the arithmetic mean as an estimator for the expected value. And why this is a good choice there for about the reasons we will also talk in this lecture. Yeah, then that you just remember how to use variance and the expectation operator, especially the expectation operator is a linear operator. This you should keep really in mind, and then of course if we transform linearly a random variable, then this translates in the variance that the constant shift is of course vanishing. No matter if I set my data around 10, or if I add to every single data point also 100, then I'm just shifting to the right my data set, and the fluctuation around my average value is of course still the same. And then of course you have to keep in mind that you have here to take out, since it is the squared distance, the square of the constant, and this, I think you remember, is then in relation with the argumentation why it is the good choice to increase the people I ask if I want to find out something about their economic issues, if you want to find out something about the relationship between the demand and prices or something like this, because we have the standard deviation as the root of the variance, and from this means then the scaling of 1 over square root of n, that your average value will be with 1 over square root of n be better in the neighborhood of the true value. To this we also come then today when we are talking about the normal distribution. Yeah, then of course again the introduction of the probability axioms introduced by Kolmogorov. in the beginning of the 20th century, and from this we can deduce all what we are talking about in statistics. From this we have deduced some rules and the so-called conditional probability, and here we had last Tuesday some examples, and having calculated the total probability as if we have our elementary events, we can calculate the overall probability of an event B as the sum of the conditional probabilities of B that AI has already happened times the probability of AI. This is then deduced from Bayes' theorem. And now we want just to do also here some examples. But I think this you also have already seen in your introductory courses. So maybe you have been also already in a casino. Then we just ask, what is the probability if you are playing roulette and in Sylvester 1988 in the casino in Constance down at the Bodensee, it really happened that at the roulette table the event 0 or 3 has occurred 9 times in a row, and that now you should calculate how large is the probability that this has happened. So at first, of course, we have to know the probability just that A happens one time, so probability that the outcome is 0 or 3. Have you ever played roulette? Do you know what it is? You have just your wheel with how much numbers? No? Well, then let's see. So it looks like this. So how many numbers do we have on a roulette wheel? Hello? No? Okay. 36, but also additionally here the 0. So 0 to 36, then we have 37 numbers. And then hopefully this is a fair wheel. What is then the probability that 0 or 3 is the outcome? Well, the probability is then, of course, 2 over 73. And now assume every single event are independent. Then What is that 9 times in the row 0 or 3 is happening? Flipping a coin 2 times, obtaining heads. What is the probability? The first time, flipping a fair coin, obtaining heads is hello? Hello? Please type it in or say something. You have passed your introductory statistics course? You don't know, flipping a coin, a fair coin, heads or tails? This would be 50%. 2 times independent events means you can multiply your probabilities. So overall probability is then P of A 9 times, and we multiply this. So P of A to the power of 9. This I cannot do, just only in my heads. So again, as we have already done, let's do with Excel. This I also always recommended, that you just open an Excel file, and there you see this probability is really, really small. So this is roughly, what do we have? 0.54, so 54%. And overall here we obtain 3.9 times 10 to minus 12. Very small, of course. So now what do you think? Now we are unfortunately only 2 students, but if we think of 2 students having birthday at the same day, just in one room, what do you think? How many students have to sit in class or to enter this Zoom room that the probability is 50% or larger that you have at the same day your birthday as somebody else in class? Just estimate. What do you think? How many? Just make a guess. No idea? Well, then let's see how we can do it. How many possibilities of the distribution of the birthdays we have? Well, we assume that we have only years with 365 days and we skip the 29th of February. So 365 days and n students. Then hopefully you know that you have then 365 to the power of n possibilities of the distribution of birthdays in a year. Well, if you take just the two of us, then of course you have 365 possibilities. I have 365 possibilities. Then you have to multiply these possibilities 365 squared. And if we have then 3, so we come to 365 and to the power of n. Well, then we can think of first one has maybe its birthday at the 1st of January. Then, if the second guy enters, not having at the same day his birthday, there are only 374 possibilities left. So, think of, assume the first student has its birthday at the 1st of January. Then, for the second student, only 364 possibilities are left. Then, of course, for the third students, only 363 possibilities are left, and so on. So then for every new student entering, we obtain always one possibility lower than before. So then for the distribution overall, not having the same birthday as some person which is already in class is then overall number of possibilities not having birthday at the same day is 365 times 364 times 363 and so on up to the number of 365 minus n. And then probability of n students not having birthday at the same day is then 365 times 364, 365 over n, divided by all possibilities, 365 to n, and this we set then to 50%, and solving for n, we obtain 23. So if you are sitting with 23 other students in class, then the possibilities that two of you have at the same day its birthday is roughly 50%. This is actually just a very standard example that you get some feeling what means independency of events. So I ask, have you done this in your introductory course? Actually, it would be nice if you communicate with me, because otherwise there's no need for me to give a lecture. But did you have an introductory course in? So you have to do your statistics introductory course, or you have it done abroad? Okay. So hopefully you have done your basics. Well, we will see. Okay. So then, total probability. Think of a small village where the postman is coming, and, well, if he is in a good mood, then with probability 90%, and he has a bad mood, and then he is late with 40%. What is the probability that he is late at any day if he is on average in a good mood at 7 out of 10 days? So, what we want to do here. For this, we can use the conditional probability. So we have probability of postman is late. This we want to have. Well, and from total probability, we have the single, the elementary events is, where do we have it? Good mood and bad mood. These are our elementary events. So then we just write down our definition of total probability using conditional probability. So this is then probability postman is late, conditionally that he is in a good mood times the probability that he is in a good mood plus postman is late condition to that he is in a bad mood times probability he is in a bad mood. Well, and now we can just use the information we have here. Well, good mood, he is in time with 90%. So then he is, if he is in good mood, late with the complementary event 1 minus 90%. So this is 1 minus 90%. What is the probability he is in a good mood? 7 out of 10 days. So times 70% plus late if he is in a bad mood, probability 40% times probability he is on average in a bad mood, 3 days out of 10. So 1 minus 70%. And overall, we obtain then roughly 19%. Okay, what else? Well, this is really important using conditional probabilities that we really know what is statistics about. So go back into the pandemic situation. Then we had this vaccination and we have our corona tests. And I think you had to do your corona tests also when you wanted to go to school or somewhere else. And there we knew that the corona test is only reliable with a specific probability. So let's then create such a situation. Event A is the patient is ill. Event B is we have tested and the test is positive. And here now we assume we have a rare illness so that we are really ill. This probability should be only 0.1%. And now we know about the accuracy of our tests that it is not 100%. Of course, your corona test, our corona test, hadn't also not a accuracy of 100%. But we know that the conditional probability of positive test given that we are ill is 98%. So if we look at this, well, then we think, well, it is quite reliable. 98%. This is a large number. But we also know that we obtain this red line in 3% of all events. But here, A bar, this means not ill. So we obtain a wrong result in 3% of the cases. Well, then in general, we would say, well, it is a quite good test. But now let's put this together. Now we want to know if the test is now positive. What is then really the probability that I'm really ill? Well, and for this, we again use the same formula as we have used it with the postman. We have our single events, elementary, events are A and not A. So ill and not ill. And this means the possibility that of PB is B given A times A plus PB given not A times probability not being ill. What is asked? Asked is P of ill conditional positive test. So this is P of A condition on B. So the other way around. We look at our test while he is positive. Do I am really ill? But we know only this probability here. And now from Bayes' theorem, we know that this we can write independence of this conditional probability as P of A, B of A times P of A over P of B. And with this, we can just calculate everything. Then we know P of A given B equals P of B given A is 0.98 times patient is ill 0.1% over PB, and PB is here given this total probability B conditional A 0.98 times P of A 0.1, 1 promille times, and now this small obtaining the wrong result 3% times not being ill, and this is almost 100%. This is 1 minus 0.1%, so 0.999. And if we calculate this, then we obtain that given these situations here, so I see a positive test, do I am really ill is only 3.2%. So this means that this is really a poor test which I have here. And this is because of this rare events which I have here. So in the end, we have a, so to speak, poor test. Because if I look at it, see this red line, that I'm really ill is, given the survey data, only 3.2%. And this was also during Corona time. This we can also apply on the success of vaccination. And you remember that the first vaccines, they came from China. But if you remember their surveys, there was around 60% of success, but conditional that you are really ill. And from this, you could really say that these vaccines which we have got from China in the beginning of Corona, that they were more or less worthless. And this you could have calculated from your statistics courses. Okay, then let's go on with the theory. I think this one we skip. Maybe we do it next week. Then let's use the next one. Oh, this is the wrong one. Sorry. Now I have to use true. Where is my... Oh, this hasn't worked. So then let's download it from my web page. Statistics. Here we are. And this one. Summer statistics lecture. Oops. Let's name this. Oh, no. Let's name this test. And then okay. So now what I want to do with you is that we switch on the review of some standard distributions which you should have seen in your introductory courses. And the first one is the binomial distribution, and I have already talked about flipping a coin. And this such a situation we have very often. Well, not the situation that every event of these two possible events is just 50%, but quite often, as you have seen here, ill or not to be ill, so the event and the complementary event, that they depend on each other just with the probability p and 1 minus p. So a random experiment with two possible outcomes, success or failure, and we repeat this flipping the coin n times. And then we want to know what is the probability if I flip my coin n times, or redoing such a binomial, random experiments with two outcomes, that I am k times successful within n, then of course larger than k repetitions of my experiment. We assume that every repetition is independent with the former one, and that the probability of success is P, and the probability of failure is, as I mentioned it, 1 minus P. Well, and then this you have done in school, where you have introduced the binomial coefficients. There, of course, since the events are independent, it is not a surprise that again we have to multiply the probabilities. So think of flipping or not flipping a coin, let's say throwing a dice, and success should be a 6 and all numbers, other numbers should be a failure. So probability to have a 6 is then 1 over 6. Probability for the failure is then 5 over 6. Throwing 3 times this dice and asking what is the probability having within 3 times thrown 2 times a 6 is of course multiplication of 2 times success, 1 over 6 times 1 over 6, times 1 time no success times 5 over 6. But then you have to keep in mind, it could be that you have these 2 successes in the first 2 throws, or in the first and the third, or in the second, this one, second and the third. So you have 3 possibilities within 3 throws of a dice to have 2 times success. So in my case, this would be then k equals 2, n equals 3, p squared times 1 minus p up to 1, 1/6 squared times 5 over 6 to the power of 1, and then 2 times success can happen 3 times, and this is of course 3 over 2 equals 3 faculty over 2 faculty over 3 minus 2 faculty is of course 3. So this is the number k successes can happen. Well, and then using this probability, using the definition of the expected value, E of x is sum over P of x times x. Then we obtain that the expected value in the binomial distribution is just n times p, and using the definition of the variance, we obtain n times p times 1 minus p. This I really hope you have seen in your introductory course, because this is one of the central distribution which we are using in statistics. So the examples we will do then together in the next week, and let's go on. Oh, this is 2 times the binomial distribution. So let's this we don't need here. this, 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 delete, delete, and delete. So this is then our task. Or we can have a continuous variable. There, the probability that x is in between some interval, we have defined this as the integral over the density function. And here you really have to keep in mind, going to a continuous random variable then means that x is a specific outcome. We cannot calculate then a meaningful probability because of the uncountability of the real numbers. Of course, let's take such a distribution f of x. The area under the distribution function then of course has to be 100%. Yeah, then let's see, just have a look at the example for a density function given by this function. First thing, introducing this with a constant a. How do we obtain then if this linear function is the density within the interval of 0 to 4? How does our density function then looks like? Of course, it is 0 in the negative part of the real numbers. Then we have a, and setting a equals 1 over 8x, we have x0 equals 8a. So at 8a, we are cutting the horizontal line. This is maybe here, 8a, and we obtain such a density function. 0 otherwise means we are here. So this area has to be 1. How do we get this? Of course, then using the definition, we have 1 equals integral from 1 to 4 a minus 1 over 8 times x dx. What is the integral of this? Can you help me? Integration you have done in school, or? What is the integral of ax dx? Oh, not ax, only a, sorry. Integral over constant. So, what is the task? Which function has the first derivative to be only a constant. Hmm. F of x equals 3x. What is f prime? Simple question. 3. Yes. F of x equals a times x. What is f prime? A. So what is the integral over a constant? The other way around. Not taking the derivative, but integration. A times x. Here we are. So then we can write down this is within our limits 0 to 4, a times x. And what is the integral over 1 over 8 times x? Again, you have to think about the question, which function has the derivative 1 over 8 times x? F of x equals x squared. What is f prime? Hmm? X squared over 16. Great. So here we are. Minus x squared over 16. And then setting in our limits. So we obtain a times 4 minus 16 over 16 and setting in 0, then of course this vanishes. So we obtain 4a minus 1 equals still 1. So 2 equals 4a and we obtain a equals 1/2. So then we can say this is 1/2 down to 4. This would be our density function. And this we also then do next week. Let's go on. Yeah, then of course what we quite often use is the so-called uniform distribution. The uniform distribution, the reason that this is quite important is that we make the assumption that something is uniformly distributed quite often in the case when we are knowing nothing about the distribution. Then quite often a reasonable assumption is that more or less every event in a discrete random experiment with a discrete random variable, we assume every event has the same probability, or here in this case, when we take a continuous random variable, then every interval which has the same length has the same probability. Well, and this means then such a density function would look like this, starting at A up to B. Within this interval, the condition that every interval with the same length has to be the same probability means that we have a horizontal line, and since we assume that integrating over our density function, the area, compare the former example, has to be 1, then of course we have this rectangular. One side is B minus A. Then the height of this rectangular has of course to be 1 over B minus A, since B minus A times 1 over B minus A equals 1. Well, and then you can show the expected value. Very surprising, we have a symmetric distribution, is just in the middle at A plus B over 2. Then maybe a little bit surprising is that this is the variance with this factor 1 over 12, but this you also can just calculating using the definition for the uniform distribution. Well, and then of course we know, since every interval has the same probability, that the cumulative distribution, this is just here from minus infinity up to some number, x is f of x prime times dx prime. So just starting from here and increasing, the area is very surprisingly just a linear line. Okay, so here also an example for next week, and then in the end I already mentioned it. Of course, there you absolutely can say the most important density, the most important distribution in statistics is the normal distribution. Hopefully you have talked about the normal distribution. This is not new for you, or? Normal distribution. You have dealt with the normal distribution in your introductory course, or also in school. Yep. The density function has this famous shape, f of x, and this Gaussian curve. Here is roughly 0.44 n 0, 1. So with mean 0 and standard deviation or variance equals to 1. Yeah, unfortunately, the formula for this normal distribution looks a little bit more complicated, this is here this exponential. Or if you take n01, inserting this, then you have n of 0,1 of x is this famous 1 over square root of 2 pi times x of minus x squared half. So where does this constant comes from? Well, this is because the integral over this squared exponential function here is just square root of 2 pi. So maybe in school you have calculated integral over minus x squared, that from minus infinity to infinity, that this is just the square root of pi. Well, a very famous result, because here you have pi, the circle number, and this is the Euler constant, which you see quite often in growth processes, because this is then the limit of geometric growth, and this is 2.71, and this one is 3.14. Maybe two of the most important numbers in statistics and mathematics, and they are depending directly to each other via the normal distribution. This is a very, very famous result in mathematics and statistics. Well, then in statistics, we are interested in probabilities, and the density function, unfortunately, don't give us the probabilities. The probabilities for a continuous function we obtain by the integral of the density function. So the cumulative, capital F. And so, unfortunately, we have to integrate this quite complicated formula, and there we have to admit there is no closed form solution, so to speak. So this is a difference between the differential calculation, so taking derivatives, and the integration. Taking the difference, we have definite rules. We always can give the exact results, calculating f prime, f double prime, and so on. The other way around, unfortunately, sometimes it's not possible to really write down a specific function, and therefore, since no closed form solution exists, and therefore this quite often we do then in mathematics, if we need this function very often in calculations, then we define just a new function defined via this integral. The same we are doing with sine and cosine and so on. Since we need this sine and cosine functions very often, we just have defined, for example, sine x is this function here with pi x, a function with this shape we defined as sine x, and here this we defined as the error function. Well, and then of course we are interested, given some specific numbers for the expected value and the variance or the standard deviation, then we just introduced, so to speak, tables. And on my web page I also gave you here the tables of needed distributions, and this here you see capital phi is tabulated as the so-called error function, and here with respect to the standard normal distribution with expected value 0 and variance of 1. So here we can then directly look it up, or of course in every software package there you have a function where this table is, where you have the numbers in behind. Okay, so, and what else we see here, and this is maybe the reason why we quite often in statistics are using the square difference with respect to the expected value, is that this measure of dispersion we find in the description of the normal distribution. So this is maybe some kind of a philosophical reason why we are using the square distance. Okay, then just by definition, the expected value is mu of the normal distribution, and the variance is by definition sigma squared. Yeah, why do we call this normal distribution? And this is that we can show mathematically that many distributions, if we are doing random experiments quite often, that they follow at least approximately the normal distribution. And especially the binomial distribution. We have talked in the beginning of the lecture today that increasing the number of coin flips, the number of throwing a dice, that this reaches then the normal distribution. And then this powerful theorem which we have very often asking people which kinds of goods you want to buy, then of course we do not know how the answers are generally distributed, because the answers depend on the preferences of the people. So actually we know almost nothing about the distribution. But then this powerful theorem, this powerful central theorem says that if we ask many people, 100, 1,000, 10,000, that then the average answer reaches the normal distribution. So, and this, I think you can imagine, is a very powerful instrument, because there, if we take many answers, asking many people, then although we do not know anything about the original distribution, we can say, asking 10,000 people, the average answer is approximately normal distributed. And what we also find is that in many biological processes, we really see that these biological processes follow the normal distribution. But for us in economics, this one is the very powerful instrument for us, since people always, due to their preferences, can say no. Even if we say, well, it would be rational to do this or this, we in the end can say, well, I say no, I do something else. But still using the Sandro's limit theorem, we can again use the normal distribution, and therefore it is also for us very, very important. Yeah, here this by hand I had already sketched for you, and then of course calculating here the different areas we obtain then for the average, for the accumulated cumulative distribution function, this shape. And then these properties of the normal distribution you should keep in mind. This distribution is fully described given the two parameters standard deviation and expected value. It is symmetrically, and going back here, around here and here, we have our turning points where the curvature is turning from a left curve to a right curve. And there it can be shown that these turning points is just at expected value plus 1 times the standard deviation. And this is then more or less the reason when we have calculated the standard deviation that we then say in general, well, given the expected value, for example, 2.5, having calculated a standard deviation of 1.2, then we say in general, well, our variable is fluctuating in between the interval 2. What did I said? 2.5 plus minus 1.2. Yeah. In general, if the variance is going up, then the distribution would get broader, so it flattens then, and of course it reaches 0 when we are going to plus minus infinity. Yeah, and then we define the standard normal distribution using expected value is 0 and standard deviation is 1. And the next one is, oops, then very, very important that, and this is then used, that given any normal distribution with some expected value or standard deviation, we can transform this distribution into a variable which is then standard normally distributed. So suppose we have some normal distribution, any number for variance and expected value. Then we redefine for us a new random variable. Remember what we have done here. This is just an application of, where did I had it? Here, of this linear transformation here. We linearly transform our variable x to z, and z is given by our original variable x minus the expected value over the standard deviation. Well, if we say y is ax plus b, as we have done in the introduction, then here it is z equals 1 over sigma times x minus mu over sigma. So minus mu over sigma coincides with our b, and 1 over sigma coincides with a. And this one is then standard normally distributed. And of course, since we are now just fluctuating around 0, then this one is the cumulated standard normal distribution function. So phi equals 1 over 2 pi minus x squared half to x squared from minus x prime phi of x up to x, or here I used c as a variable. Well, and then we can ask for what we are interested. Our random variable is smaller than some specific value small x, that this translates there. We recalculate from now given set backward our x, then we know that this is x, and this of course then translates in z is smaller than our standardized mu limit. And this means our general normal cumulated distribution function we can directly express via the standard normal distribution function. So this is standard. No, this is the normal distribution, and this is standard normal distribution. And since we have this direct dependence, it is enough when we are just given only the numbers for the standard normal distribution. Yeah, this is just the illustration how we now calculate our probabilities. Again, general definition, the probability that x is in between some interval just means the area under the density function in that interval. Well, and then this we later on will need when we do hypothesis testing, because quite often we set some general limits where we say we want or we ask, given an error probability of 1 or 5%, given my data set, is my hypothesis that, for example, people will buy this good in a price interval of 3 to 5%? Is this answer that they are buying this good then true? Given an error of 5%, for this we then have to know, when we have assumed approximately a normal distribution of our random variable, then we are interested in the interval when x is lying in this interval with, for example, 95, 90%, or 99%. So, using this interval from minus 6.4 to 6.4, then this area here is 0.9. If this area should be 95, and this is maybe the most often used number, actually Fisher, in a very famous statistician, in the beginnings of the 20th century, he just used this 5%. Unfortunately, many people then say this 5% is some central number in the world, and then everybody talks about, well, my result is statistically significant if my hypothesis is true with 95%. Well, this is, I think, even a mistake, because this limit of 5% is chosen just by one man 100 years ago. I think you always have to think about your question, about your experiment, which is the right level. Well, quite often maybe it is 5% that it is a good level as an error, but it has not to be in general that it is the right error. Nevertheless, many people use this 95% probability, and therefore it is good to know that then the limits in the standard normal distribution are roughly minus 2 to 2 or minus 1.96 to plus 1.96. 98, this means the right one is 49%, the left one is 49%, and this is maybe the second mostly used 99% reliability. Then the limits are 2.58. Well, these numbers we will then later on in this lecture see very often. So please keep this table here in mind. Okay, another example for the next week. And then, the so to speak last property of the normal distribution. This is also very nice, that if we have independent events, that then the accumulated distribution of the sum of some random variables just splits into the property that we can just then sum up the single expected values, and even more important, we can sum up the single variances in order to obtain the overall variance. And this property we also very often will use. We will use in this lecture, and here in the theoretical exposition I will give you also this central limit theorem. Well, we already said the arithmetic mean calculated as the average sum of our single variables, and then we can calculate the overall expected value is just mu, and here you see the scaling of the variance with 1 over n, and this means this scaling of the standard deviation with 1 over square root of n. And having standardized now our variable, means that this is here now scaling with this square root of n. And now if we move this n to infinity, then we can show in general that this random variable, where we at first do not know how it is distributed, we only know that the starting variables are independent, identical and independent distributed, that this in the limit moves to the standard normal distribution. So here in the limit we can use the standard normal distribution, and this we will then also do. Okay, so we are done for today. And for next week, then next week we will meet on Thursday. I want you that you try to calculate the examples which we had here in the lecture. Tasks like this you should have seen, of course, in your introductory courses. And on my webpage, I gave you here also some exercises. Please do them also over the next week, and we will meet then on Thursday doing these exercises here together with the example within the lecture. Yeah, thank you very much for today.